Setting up a computer network might seem like a straightforward process, especially if you have some experience of setting up a small or a home network. After all it takes is just plugging some devices into a switch with some cables. But what defines and makes high-performance systems is the careful design of every aspect of the overall environment. Nothing should be random or left to chance, and that includes the choice of network topologies. But wow, Bryan's used a big word, topology. What is a topology? A topology in networks is defined as the physical or logical layout of a network. That is, how the nodes are placed and how they are interconnected with each other, as well as how communication or data transfer might take place along that network layout. Once you realize how much there is to setting up and managing a network, it quickly becomes apparent just how configurable the network really is. It is no longer a simple act of just plugging in a cable. It's about the choice of the cable, the placement of the systems, and even the management of the data communication. One decision that you typically have total control over is the network topology. When you design your system, you have a few options to choose from, and this will determine what hardware you buy and also how much you will spend on that hardware. The first topology that we're going to cover is the mesh topology. This entails at least some set of the nodes being interconnected to many other nodes in the mesh. It offers link redundancy, and it does give better network performance since communication is distributed, but it can be complex and expensive to get it right. There's a big factor of pain versus gain in this setup, because no matter how experienced you are with this topology, it can easily get complicated. The image here shows the obvious reasons for the name of our next topology, the star network, or star topology. It's a common network setup where every node connects to a central device like a hub, a switch, or a computer. The central network device then acts as a server, and the peripheral devices are the clients. There is centralized management of the network, and it's easy to add another computer to the network, and if one peripheral node were to fail, the rest of the network continues unaffected. In this case, the bottleneck will be the central network device, and that's where the root of the TCP incast problem arises. But worse than that, this is also the single point of failure in your network. This is probably the simplest network topology that you can use in an HPC system, and on a very small cluster with 2 or 3 or 4 or 5 nodes, you would typically have them arranged like this with a switch in the middle. The bus topology, also called the line topology, has each computer or device connected to a single line or a single backbone. This is effective on a small network and uses less cabling than a star topology, but troubleshooting failures is difficult and it is terrible with larger networks. In fact, this was the very first network that I ever used with carrier sense multiple access collision detection, and it is painful. So I would say avoid it. Now, another very popular topology with small HPC clusters is the ring topology. Now, it's called ring topology because the network looks like a circle. Each network device is connected to 2 others, like points in a ring. Just like the social game that's all the rage at varsities nowadays, pass the parcel, data in a ring network is usually passed from one device to the next until it reaches the destination. Typically it is done unidirectionally. That means either all clockwise or all anti-clockwise to reduce the risk of packet collisions as data is shifted in opposite directions on the network. The major risk with this topology is if one connection is broken, the network will be affected. This is definitely a fan favorite for the budget conscious in the competition, and a word for the wise. Although this is an appealing option for a small cluster design to save costs on a network device, the pain of getting this working sometimes outweighs the potential gain. Teams with switches don't dig their own ditches for days, whereas teams without switches run the risk of a slow or a late start if things don't work from the get-go. So all I'm saying is it's not a bad option to consider this, but you have to weigh the pain versus the gain. And finally, I'm going to include the jellyfish topology just for a bit of extra information. It won't be something that you need to understand, and in fact, it's not something that many others actually are familiar with. The jellyfish topology is effectively an unstructured network that uses a randomized topology for interconnection in a data center. You just pick a random pair of switches with free ports, then you link up those free ports, and then you continue to do this until all the links on all the ports on all the switches are exhausted. It's been shown that this design can support up to 25% more servers with exactly the same equipment used in rival topologies, with over a 90% better network capacity overall. This higher capacity is achieved because they're using shorter paths between all the servers. And, boys and girls, I present to you, for the final time, the jellyfish topology.